Okay, well, good morning, team. We'll make a start. So, we thought we'd start off with looking a little bit of a slip and slide. So, is this something you'd be interested in doing?
Looking good. How do you like it? I love it. It's gonna be scary.
So, I think the guy up there was putting on some detergent. He broke his nose. So, looking at the physics we looked at on Friday, do you think he's going to make it the whole way round? Okay, do you remember what we figured out on Friday? What was the minimum height we needed to be able to get around? 2.5 R. And is that 2.5 R? Okay, so you're saying that this is R, and so it needs to be 2.5 R to go around. Does he look like he's 2.5 R? No. Where did the 2.5 R come from? Okay, so he's going to have some kinetic energy at the bottom. And does he have to have any kinetic energy at the top? Can he have a velocity of 0? No. He has to be moving, because what happens if he's got a velocity of 0? If he's got a velocity of 0, does he have any centripetal force? No, if he's got no centripetal force, there's no force kind of spinning him around. What is the least? Do you remember what the smallest speed we have to have at the top is? Square root GR. Do you remember how we got square root GR? So V min at top. And we said that at the top, the centripetal force must equal the, our weight force. And so we get mv squared over r equaling mg. And we cancel our m's. And we get v squared equals gr. So v min top equals square root of gr. And that's all because that is the condition at the top. And so he has to have that much speed. And we said if we worked out our mass times gravity times height on this side, and we worked out our mass times gravity times height plus a half mv squared, that we have to have that speed square root gr, and the height we have to have here has to be 2.5 r. Is he going to make it around? Shall we watch? I believe there's some blood, so if you're a bit squeamish. Did I push record? Yeah, that's good. Did he make it around? There's quite a significant difference between, like, he might have made it, I don't know, an hour and a half. How could we get around then? What could we do differently to help him get around? Yeah, Ensign. Increase the speed. Yeah. Sorry about. Okay, so now we've got a mattress to make it have less blood. What's he got attached to him? A rope, and that's attached to a car, I believe. Oh, was that the whole way around? He's excited about it. So what effect does holding onto a rope behind a car do to help you get around the loop? It increases your velocity, so you've not just got gravitational potential energy being converted to kinetic, and part of the issue there is that you've got some going into heat and sound. You can hear them going down the ramp. This also essentially gives them more kinetic energy. It provides an external force to help them go faster. There we go. We made it the whole way around. So we still connect at the top. And so what we have at the top is he's got his weight force going downwards, and he needs a force towards the center to help him change direction, the centripetal force. So when the weight force at the top equals the centripetal force, he goes the whole way around, and so he's traveling at or faster square root gr. And does his speed change as he goes around the circle? So going pretty fast there, pretty blurry. not as blurry. And he doesn't really speed up that much because there's a fair amount of friction. There we go. What a way to start out. Well, there's only so high your roof can be, right? Like, they had fun before. Okay. If we remember, on Friday we spent a bit of time looking at this marble doing the loop-the-loop. We'll wait for YouTube to load. And we said that it was 2.5 R. Is it going to make it the whole way around at 2.5 R? Who says yes? Does it account for friction? And is there going to be friction? And so is it going to make it around? We'd expect it not to, because we assume that the friction is going to have an effect on it. And what do we know? It doesn't make it the whole way around. It does come up the other end, but this is in slow motion. We see that it actually, if I pause the video there, it loses contact. So it's actually going slower than square root GR. But amazingly enough, it lands back on the track and gets up. So what do you reckon the height would be to get it to go around, fully be in contact? It's going to have to be a little bit higher. And I think they work out it's at 2.7 R. And that extra 0.2 R of height of gravitational potential energy is because of friction. Yep. And so the animation we were playing with on Friday didn't account for friction, which is fine. Oh, sorry, if the video is more clear, there's a little clicking thing that it clicks into. Yeah. Hopefully that didn't crash my computer. I think it did. So here's a little animation that's animating, showing a bob being swung around in a circle. And so this is kind of modeling a bucket being swung around our head, or a keys being swung around our head. So it's non-uniform circular motion, and we're seeing this red arrow. So this red arrow is essentially saying the tension force, and we've got a blue arrow. Does the size of the blue arrow change? So the length of the blue arrow doesn't change. It's still just the size of an arrowhead. Does the size of the red arrow change? Yes. Where is it the biggest? It's biggest at the bottom because it's got weight force going down and it's got the centripetal force going up. And the formula for centripetal force is mv squared over r. And at the bottom, our v is the greatest. So I don't know if I can write on here. I can. Wow. So mv squared over r, and the v is the biggest at the bottom. And so we've got the largest centripetal force. And we've also got weight force going in the opposite direction. So if we add those two together, we get a huge tension force at the bottom. But at the top, the weight force is going down, which actually provides the centripetal force. But you still see there's a red tension force. What does that tell you about the speed of it? Is it going faster than square root GR? Is it going square root GR or slower? So if I try and draw it, oh, what a horrendous drawing. Let's just get rid of that. Okay. It's going faster than square root GR because it still has tension at the top. So this is going greater than. Yeah, I can try. I can just go to the next slide and it gives me this lovely diagram. So the resultant force acting on the body must be given by the centripetal force. And so you see that the reaction force or a tension force can be equal to weight. And if that's true, that's going to give you your square root GR. You've got a force going inwards and a bigger force at the bottom. So all I need you to know is that the force at the bottom is bigger than the force at the top. And so we spent a little bit of time playing with this kind of idea. Can we go sideways? Oh no, that wasn't meant to. And the answer is yes, we can go sideways. because a component of that weight force is given in the tension force. Can we make it 90 degrees? No, we can't. We see that the water, if I could zoom in, the water is actually level in there because that support force is pushing back on the water. And we can also do a vertical circle as well, but I don't think that's an example. Not today. So there's two different scenarios of the same thing. One is keys or an object on a string. One is an object going around in a circle. And so we see the yellow arrow. So the yellow arrow is essentially the support force from the ramp. And you see how it's really big at the bottom and gets smaller and smaller till it disappears at the top. And so this is traveling around at the least speed possible. I'm now going to show you the other side. And you see that it goes to 0 before it gets to the top. And so, Tiffany, what we see is that the car falls off the ramp. Okay, and so we need to have that square root GR for it to make it the whole way around. Cool. I'm going to disappear out of that. And somehow something happened. We're going to have a go at the question in our booklet. So on page 30, there's one about a little mini bike. So we'll watch the little video and then we're going to have a go at the mini bike on page 30. Okay, so clearly he fell off. Why did he fall off? Yeah, so you kind of see that there's actually a lot of force as it begins to go up. And so his suspension begins to get squished in and he's not quite used to that. You see that the whole frame moves. You see that like the whole ramp vibrates a lot because there's actually quite significant support force there and he falls off. That was just dumb. He drove off the wrong side of the curve. They're a much longer run up this time, and so that would mean that he's going a bit faster. Going faster means at least he can get to square root GR. If he goes faster than square root GR, that's fine. There's just a support force at the top. And then you see that his bumper is basically touching his back wheel because there's quite a large amount of support force there, and the result is he once that support force kind of is no longer needed because he's no longer going around a circle. So if he kept going around a circle, he'd be fine, but he's not doesn't keep going around the circle, so he flies off. Awesome. And so if we see we have a question here. So Charlie and his mini bike have a combined mass of 90 kgs and they approach a loop-to-loop ramp at 8 meters per second with a radius of 1.2 meters. One, determine the weight force of the rider. So that should be nice and easy. So for number one, we're using weight force is mass times gravity. Where is the reaction force from the ramp the greatest and the least? In order for the biker to complete the loop at the slowest speed, the centripetal force required to keep him on the loop is required to equal the weight force. See if you can do the calculation to show me square root GR. Do some energy calculations. Essentially everything we've been talking about for the last little while. Okay, let's have a go. So if you've got 4.1 and 2280 joules, then you can move on. We head into SciPad, so 137, 138, 141, 142. If not, I'll quickly go over those answers so that we can get there. So determine the weight force of the rider for number one. So the weight force is just going to be mass times gravity, and it's going to be 90 times 9.81, which gives us 882 newtons, and so that's his weight force. Determine where the reaction force or the support force from the ramp is the greatest and where it's going to be the least. And so if we have our ramp at the bottom, we're going to have a weight force downwards. And at the top, we're also going to have a weight force downwards. But we're going to have a large centripetal force here, and here the centripetal force is in the same direction. So Fc can equal Fw, and so the net force, or the total reaction force here, so F reaction can actually equal 0 when V equals square root GR. Okay, so the reaction force is least, Fr is least at the top, but at the bottom, the reaction force is actually going to be Fc plus the negative of F weight, which is actually going to be really large. And so the F reaction force is going to be large at the bottom. In order for the bike to complete this at the slowest speed possible, the centripetal force required to keep him on the loop is equal to the weight force. Calculate the slowest speed possible, and I've just done that earlier in the lesson. So it's just V equals square root GR, and so it's square root of 9.81 times 1.2. And the way we got the square root GR was Fc equals Fw, and we get a speed of 3.4 meters per second. Calculate how much EK he has entering the loop. And so another way of saying this is, what is E total? And so he's going to have, going into the loop, how much kinetic energy do we have? Really what we're saying is, what is the EK top and how much EP has he gained? And the EK going in is going to equal EK top plus EP. And so this is going to be a half mass times velocity squared plus mg2r. And so it's a half times 90 times the square root of gr all squared. And actually we already know that number from an earlier calculation. And that number was 3.4. And then we're going to go 90 times 9.81 times 2 times 1.2. And so what have I got? I've got the weight force, the speed at the top, and then the amount of gravitational potential energy. And if we work that out, we get 2880 joules, 2880 joules. And so that's the total energy going in. And then the last question says, will he make it around? So he's traveling at a speed of 8 meters per second. So for question number 5, will he make it around? And so will I go EK equals a half mass times velocity squared, half times 90 times the 8 meters per second that he's got. And if this number is bigger than the number above, do I know what that is? 1. Oh, I've done that wrong, haven't I? 21168. 21168. Sorry, so that number there was 21168, and this number here is 2880. And because 2880 is bigger than 2116, he makes it around. Can you? Yep. So you can have that comparison. Maybe you could have a little bit more. He makes it around. But this is the EK he has going. He doesn't have any EP when he's driving on the ground going into the ramp. Yeah. So if you're going along the flat going in, you don't have any EP. So he makes it around because he has more energy than required. Something along those lines. Yep. And so basically he makes it around. And you could have done a comparison and said, well, 4.1 is greater than 3.4. If you wanted to work backwards and work out what's the actual minimum speed going in. Yeah, so you can play that a number of ways. Basically, yes, he's got enough energy. He's got essentially an excess energy, 760 joules of additional energy that he didn't actually need to make it around. So yes, he makes it around and he's actually going faster than that minimum speed that he needs. Cool. So the rest of the work is on OneNote. So today, term 2, week 6, Monday, we're going to just be doing some consolidation now from SciPad for the rest of today, and then tomorrow we'll see if we can look at gravity.